Good afternoon, all of you. My name is Nitin Tomar. In today's session, we'll learn about some linear algebra techniques that are involved in the numerical analysis. In the last class, we saw the analysis technique that are involved in the numerical analysis. For example, we saw the definition of the limit and continuity. Then we saw, or we have a rather profound discussion about the Rolle's theorem, location of roots theorem, then bisection method, etc., etc. And as a consequence of that, we saw some problems or some applications of the previous theorems. So here, as we know, numerical analysis, one of the main aim of the numerical analysis is to put theory into application, and one of the most profound theory that have been developed is the theory of linear algebra, that is the theory of matrices. So in this session, what we'll do, we'll discuss some linear algebra and then we'll see some applications of that in the numerical analysis. Okay? So we start. So this is lecture 2. Linear algebra, or rather I will write as numerical linear algebra. So first of all, what we'll do, so in this discussion we study the methods for solving system of linear equations, and an important direct method is the well-known Gaussian elimination method. After a short introduction to the linear systems, we discuss these direct methods in detail and we'll see some examples of that. So we start with the system, okay? Then we'll see. So a general form of a system of n linear equations in n variables is given by the following. That is a, so I'm writing the system. So variables are x1, x2, xn, okay? So any equation, it will be of this form. And because we will have n equations, so we will write another equation, the rest of the equations as follows. So on and so forth. So then finally it will be now here the assumption is, see, in this lecture, in this discussion session, what we'll see how to solve n linear equations, okay? So, and we'll assume that throughout the session, we assume that Oh, okay, let me write it like this, where the coefficients aij and bj's are real. Okay, so these are the real parameters. Now note that this n linear equations, this can be written as the above system of linear equations can be written as a11, a21, then an1, a12, a1n. So what we are doing, we are writing the coefficients of the above system equation by equation as the row of this matrix. Okay, an2, and x1, x2, as b1, b2, bn. So this matrix, okay, now this matrix we write it as A, okay, then this column vector is written as, so rather I'll denote it by some fancy color. So this matrix is written as A, then this column vector is actually X, then it is and finally here we'll have, okay, we'll denote this vector by B. Maybe I should write it like this. So this system that we have, it is called a system of equation. So here note that the matrix A is of size n cross n, right? With entries of the form Aij. Now this column vector, this is, okay, let's say this is point 1. Point 2 is the column vector x, which is nothing but x1, x2. So we write it in a n tuple form, and this T stands for transpose, okay, which transpose means basically every row becomes a column and vice versa. The column vectors are, there are two column vectors, number 1 x and number b is b1, b2, bn transpose. See, in every cases, this will be an unknown vector. This is the aim. This is what we'll be able to find. That will be our aim, okay? Unknown. And this vector b will already be, this vector b will be given to us as a part of the information. Okay, so this vector x will be unknown, so we have to find x. Okay, so what is the aim? The aim is to find this vector x, this column vector x, such that ax satisfies b. Okay, so if A is an n cross n matrix, x is an n cross 1 matrix, so we know the size of B will be n cross 1, right? Now what do we do? Now here comes the linear algebra. Linear algebra. So we have a very famous theorem in linear algebra whose proof we'll see. Okay, so I'm going to write that theorem. So let A be an n cross n matrix hello Thangeshwaran, can you hear me? Am I audible?
Sir, audible.
So okay, let us revise what we have done so far. So our aim, so this course is numerical analysis. Okay, Thangeshwaran?
Yes, sir.
So what according to you is numerical analysis? Have you done that subject, or is it your first time?
Yes, sir, first time.
Oh, first time. Okay. So as you know, one of the main aim is to solve in mathematics is to solve a system of equations, right?
Yes, sir.
So what are the easiest one? The easiest one are the linear equations. Okay. So for example, in your class, let's say 10, you must have solved this kind of equation: x plus y equal to 0, x minus y equal to 1, right?
Yes, sir.
So these are called linear equations in two variable. In today's class, we will see a method known as Gaussian elimination method to solve a general system of n linear equations in n variables. Okay. Now, can you see this system written? This system 1, let's say. Okay. Now, how
Okay,
does any equation in n variable look like? It will be some equation in n unknown variable, right? Let's say x1, x2, xn, and it is just a linear combination of those variables, right?
Yes, sir.
So the coefficients are a11, a11, a12, a1n, and the variables are x1, x2, xn. So if you are having any problem, then just keep linear equations what you have done in class 10th in mind. Just put n equal to 2 there, okay? And for it to be an equation, we must have something on the right hand side also, correct? So that is our b1. So this is our first equation. Similarly, for the second equation, we'll have a21x1 plus a22x2 up to a2n xn equal to b2. Okay? And you keep on doing
Okay.
that until you reach the n equation. So how many equations are these? See, 1, 2 and n, right?
N equations.
N equations, right? So the coefficients are real, okay? These aij's and bj's, these are the real numbers. We are not doing anything in complex field.
Field elements.
Yes. Now this system of linear equation, it can be written as in this matrix form given in 2, right?
Yes, sir.
No, don't say yes. If you have any doubt, please ask. You can ask how. Then we can solve this system, okay? See, when you multiply, see, this is an n cross n matrix, and this here we have n cross 1 matrix, so the result will be n cross 1 matrix, right? So what do you get when you do this computation? In matrix multiplication we do something like this, right?
We get first equation.
We get first equation, correct, very good. If we do
If
like this,
shown
then
as second equation,
yes, and so
like
on and so forth, right?
okay, sir.
Yeah. So ultimately the problem of solving a general system of n linear equations in n variables, this is just a metric system, right? So matrices are coming into picture. Am I correct?
Yes, sir, correct, sir.
Yes. So this system we can write it as this ax equal to b, where a is this matrix with aij's and as the entries. This small x is the column vector and b is the column vector on the right hand side. Okay. So this is what we have done so far. So if you have any doubt, then you may please ask.
No, sir, no, sir.
And I would really appreciate, because no one is here, you and I are just here, so you can ask freely. Okay, you can consider it as a private
Sir,
session also.
sir, problem solving session link is not there in website, sir. So that no one.
This link is
Yes, sir.
not there,
Yes, sir, yes, sir.
so
Just
that I cannot do anything about, because I have forwarded that link to the authorities. Okay.
okay, sir, okay, sir.
Yeah. But anyway, somehow you are here. I forward you to that link, right?
Okay, sir.
Yeah. So I want you to make the very use of this opportunity, because no one is here, so you can stop me. Okay.
Okay, sir.
Yeah. So we remember we have this system to solve. Okay, ax equal to b, where a and b will be given, correct? Because we have to find x, right?
Column vector we have to find.
Yes, this x is for the unknown, right?
Yes, sir.
Yeah. So let us recall a theorem from linear algebra whose proof we will see. So let A be an n cross n matrix. Okay, let's not write under the theorem. And B be this column vector. Rn means it's a column vector, right?
Yes, sir, okay.
Yeah. Then the following are equivalent. Then the following are equivalent. Number one, okay, determinant of, okay, let us, determinant of A is not 0. Second, Ax equal to B has a unique solution. Ax equal to b has a unique solution x for every b, okay, in Rn. Okay, let us not do like this. We just write this. Then the following are equivalent. Third, Ax equal to 0 has a unique solution. You must have seen these statements before, right?
Yes, sir. Already seen.
Yeah, but we'll do the proof. And finally, A is invertible. Okay? What do we mean by invertibility? That there exists a matrix B.
Determinant of A non-zero.
No. In that sense, we are not saying. Ultimately, they are same, but we are saying this. Okay?
Okay, sir.
By definition, invertibility means this, right? By the definition that there will be a matrix B such that
Yes,
AB
yes,
equal to
yes.
BA equal to identity.
Okay. Matrix multiplication. Multiplicating
Yes.
S.
Yes.
Yes.
So let us see the proof one by one. Okay. So let us prove first 4 imply 3. Whatever is coming to my mind, I will prove. Okay.
Yes.
4 imply 3. 4 imply 3 is easy, right?
Yes.
How do you do that? So what do we know? That A
All
is
the
invertible, right? This is given. Step by step. The only way to do maths, a good way to do maths is to write everything. Okay?
okay,
So
sir.
what does it mean? That is
A is invertible. If A is invertible,
there is no let
all
us there is a n cross n, there is an n cross n matrix B such that AB is identity on n cross n identity matrix and it is same as BA. Okay?
yes.
Now let Ax equal to 0 for some x in Rn. Okay? Then what
Okay.
does it mean? Then if you pre-multiply
B,
B both
B. Yes,
sides,
yes.
it is obvious, right?
Obvious.
So you will get Bax is B times 0, but B of 0 is 0, right?
Yes.
So this, but BA is x, so x is 0. So not only it will be a unique solution, the unique solution will have to be 0, right?
Yes, sir.
Yeah. So I should write Ax equal to 0 implies x equal to 0. Here I will write in particular. Now how about what about 3 imply 4? How do you prove 3 imply 4?
3.
See, this is linear algebra.
Yes, sir.
So okay, let us go step by step. What are we given? We are given that so given is this fact
Uh,
that the equation x equal to 0, oh sorry, ax equal to 0 has only the 0 solution. Thangeshwaran, please mute your mic. Has only the 0 solution, which is x is 0. Now you have to show what? That there is a matrix B such that AB is identity is same as BA. Okay?
Yes, sir.
Now see what we'll do, we'll imply, we define something. Okay? So we have to construct B. Remember this. So define E1 to be this column vector. You know this column vector, right? 1, 0, 0, 0. And how long is this? N cross 1. E2 to be,
0, 1,
yes,
0,
0,
0.
1, and you keep on doing this.
Standard basis, sir.
Standard basis, exactly. 0, 0, yes, these are called the standard basis, or you can see these are the columns of the identity matrix, right?
Yes, sir.
Yeah. Now, can I say, just a minute. So, can I say that then the equations, so we consider Ax equal to Ei. So, this is one equation, right?
Yes, sir.
So, what should be the solution? It will have a unique solution.
I think
Why? See, because if it has, because, okay, I'll tell you. For how do we prove this? So let us say there are two solutions. Okay, because let Ax equal to Ei, and there is another solution y. Okay.
okay.
Now can I write A of x minus y is 0?
Yes, sir.
But we know by given hypothesis x minus y has to be 0, right?
Yes, yes. For assumption.
Yes, this is given. Okay. So
Yes.
what does this imply? This implies x equal to y.
Why?
Now, so this much you agree, right?
Yes, sir. I agree.
Let the unique solution let me put it like this. This does not imply x equal to 0. Okay, yeah. Let the unique solution be xi. Okay. So what we are saying, anything that solves this equation, the solution is x1. Okay. X equal. Are you getting my point? The notations I am trying to explain.
Yes, sir. Yes, sir. I agree.
Something like this I am trying to say. Yeah. So what do we do? We construct a matrix B define a matrix B as this. So remember, each of this is a column vector, right? x1, x2. So each of this is a column vector, right?
Yes, sir. Column matrix.
So what is the size of B? Can you tell?
N by n.
N by n, right? Now you tell me what will be AB.
I.
I. Why? Because it will be AX1, AX2, right?
Yes.
AXN. Am I correct? And what is AX1? It is E1, it is E2,
Yes, yes.
it is En.
Nice.
So this is In. Is this clear?
Clear, sir.
Okay. So hence B is the right inverse of C. Correct?
Yes, right side multiplication.
Can you find the left inverse also?
Yes, sir.
How?
Similarly, x is equal to E1. X is equal to E2. Similarly,
See, do you know this? If A has a right inverse, then it has a left inverse. If a matrix. Do you know this?
little bit, sir. Yeah.
Oh, okay. Okay, then let us prove this. Little bit, See, now I am writing in, okay, let me use this green pen for the B, okay. Now, let us assume that Bx is 0, okay. Then can I say x is 0?
Yes, sir.
So this property also follows for B, right? The given hypothesis.
Yes, B also satisfies.
The given hypothesis also holds for B. So when it was holding for A, what was the conclusion? That A has a right inverse, correct?
Yes, sir. He is right inverse.
So if you repeat the argument above, we repeat the argument above for A, for B instead of A, and can I say that we get that there is a C, there is an n cross n matrix C, n cross n matrix C, such that BC is identity. Am I correct? See, when the given hypotheses were true for A, we got the right inverse B. Now if it is true for B, then we'll also get right inverse of B, which will be C, some C, correct?
Okay, sir.
Is it clear? Please tell me if it is not clear.
Sir, once again.
See, when Ax equal to 0, we had x equal to 0, then what did we had? We had that there exists B such that AB equal to identity, correct?
Identity, yes.
Now what did we prove? That B, even if Bx is 0, x is also 0, right?
There exists C, AC is equal.
So using
This,
same
this is
argument I
equal
can
to.
say na, that there will be a right inverse of B also.
Equal to M. Okay.
Is this clear now?
Clear now. Yes, sir.
Okay. So see, AB is identity, right? This was given, correct?
Yes, sir.
Now if you multiply both sides by C, what do you get?
C.
But BC is identity, so you will get A equal to C, right?
Yeah.
So actually, not only AB is identity, BC was also identity, but C is A, so this is true, correct?
Yes, sir.
Okay, and we are done, right?
Then AB is equal to B.
Okay, so hence A is invertible. Okay, I hope this is clear.
I clear, sir. Nice.
So, what do we have? We have that these two equations are same. I mean, these two are same. 3 imply 4 and 4 imply 3.
Okay. 3 and 4 are if and one if statement.
Yes. Can you prove with this for 2? So, does 2 imply 3?
Mm.
See, logically think, if for any b it has a unique solution, then in particular for b equal to 0, it will have a unique solution, right? Okay, let us write it
Sir.
step by step. You don't need to get confused. Okay, we have a lot of time. I mean, at least I have a lot of time. You can go whenever you want. Okay.
Theorem proof I am not familiar, sir. Proof.
Yeah. Okay. That is okay. That is not very dangerous. Okay, but try to understand what I'm writing. Okay.
Yes, yes, sir. You are telling very nice.
See,
Last proof.
the thing is, if you know what to do in maths, if you know what to prove, then half of the battle is won. Okay. See, the problem is, Thangeshwaran, the problem comes when we are trying something but we don't know what are we trying to prove. And this is exactly where the mistakes happen. Okay, so the one way to do what I believe is to write everything explicitly. Okay,
Okay, sir. Okay.
don't be afraid of writing in mathematics. So,
Okay.
what are we given? For every b in Rn, this the system Ax equal to b, this is given, right, has a unique solution. Has a unique solution. Is this okay? Do you
Yes,
agree
sir.
with this?
Yes, sir. I agree.
Okay. Now, what do you have to show? What do you have to show? You have to show 4, right? What is 4? Ax equal to 0 has a unique solution. Has a unique solution. What is the unique solution?
X is equal to 0.
So, can you prove it? Just try. See, putting b equal to 0. Okay, you see the only difference is you
So
just put.
suppose Ax not is equal to 0 when X is equal to 0. Contradiction method. Try.
Contradiction, ax equal to 0 and x not equal to 0, but that won't lead us anywhere. See, the easiest way is, you have this given, right? It is saying for every b, ax equal to b has a unique solution. So in particular, when you put b equal to 0, ax equal to 0 will also have a unique solution, yes or no?
Yes, sir.
See, what is it? If I am saying you, okay, Thangeshwaran, you can eat anything. Okay, it means you can eat mango also, right?
Yes, sir.
So this is same as saying this. If ax equal to b has a unique solution for every b, then it will have a unique solution for b equal to 0 also, correct?
Yes, B is equal to 0 also particularly.
Yes, in particular. Very good. In particular. Ax equal to 0 has a unique solution. Ax equal to 0 has a unique solution. Okay. So one solution we know, right? Since
Yes, sir.
x equal to 0 is one solution, right? You put x equal to 0, what will be a times 0?
0.
0, yes. So one possible solution of ax equal to 0. Now we know one possible solution is 0 and it has a unique solution. So what will be the unique solution?
X, X is equal to 0.
Yes, yes. No, you
0
don't
vector.
seem very confident. Why?
0 vector.
See, 0 is one solution and we are saying there is only one solution. So
Yes.
this implies that the one solution has to be 0, right?
Yes, unique solution and that is 0.
Yes, exactly. Now we prove 3 imply 2. Remember 3 imply 2, 3 is same as 4, right? We have
Okay.
proved. This actually we have seen in the argument when we are using 3 imply 4. If ax equal to 0 has a unique solution and let ax equal to b has two solutions, x1 x2. See this argument, you remember here, you know this argument, right?
Yes, sir.
So this is precisely the argument for 2, right? Okay, let me just write. Assume that 3 holds. Okay, assume that 3 holds. 3 means you know 3, right?
Yes, exactly.
And we have to show ax equal to b has a unique solution. Has, see this exclamation mark na in mathematics, it means unique. Okay,
Yes, sir. I know. That's enough.
so if ax equal to b, we know 3 is same as 4, right? Which means a is invertible, correct?
Yes.
So you multiply it with a inverse.
A inverse B. Okay.
So what does it mean? That x is equal to a inverse b.
B.
So this is first point. Second, so it has a solution. Okay, it has a solution given by a inverse b. Now y is unique, so this is called the existence part. We showed that there is a solution. Okay,
To show uniqueness.
yes. So and this is a very standard thing in mathematics. First you prove the existence, then you prove the uniqueness. Okay, let us say ax equal to b is equal to some ay. Then what does it imply? It implies ax is same as ay. You multiply with a inverse both sides.
Then X is equal to.
Then x is same as y. Okay.
Yes, sir.
So up until now, what do we have? So this proof is long, huh? This proof is easy but long.
Yes.
I hope you are getting the proof. So up until now we have proved that 2, 3 and 4 are equivalent.
Yes,
Correct?
sir. Correct.
Yes. Now, so we have to prove determinant of A is non-zero if and only if 2 or 3 or 4.
Remaining three statements are equivalent.
Huh?
Remaining three statements are equivalent to 1.
3 is equivalent to 1. Why?
Remaining all threes are equivalent to 1.
Why? That is the proof you have to provide.
Yes.
See, okay, let us do one by one. Huh? Again, see, there is no need to be confused if we can write everything. Okay. Okay.
Okay.
If I prove 4 imply 1, then and 1 imply 4, then that is done, right?
Okay.
Because 2, 3, and 4 they are equivalent.
Already equivalent.
Yes. Yes.
Already proved.
Yes. So what do we assume? We assume that A is invertible. So what does it imply? Therefore,
A,
A
B,
A inverse is identity, right?
A inverse is equal to A.
Now, if you take determinant both side, what will you have?
Determinant of In is 1.
1, exactly. And what is determinant of AB? It is determinant of A times determinant of A inverse, right? You know this.
Yes. Yes. Yes.
Now, see, if determinant of A is 0, then LHS will be 0, correct?
Correct, sir.
So, can I say from here determinant of A is not 0?
Yes. Determinant of In is 0.
This is, see, determinant A times something is 1.
Yes,
Oh,
sir.
so that determinant of A cannot be 0, correct?
Cannot be 0. Yes, I understood, sir.
Yes, exactly. Thank you. Now, what do we need? We need 1 imply 4. So, have you heard of Cramer's rule?
Sir?
Cramer's rule.
Yes, sir. Cramer rule.
Oh, okay.
I think
Ah, you have heard a
del
lot
x,
of things. You
x,
know
x
things more than me. Good.
del x by del. That
No, this formula like Cramer's rule. In one form, it is says that A inverse is actually 1 upon determinant of A, or this is more precisely it will be A times adjoint of A. Do you know what is this?
yes, sir.
What does it come?
Adjoint of A times A.
Times identity, right?
Yes.
Am I correct? This you know, right?
Yes, sir. In
So,
sir,
for
physical.
example, let us see. Okay, how much do you know? Let's say A is 1, 2, 0, minus 1. Okay. Now, can
Okay.
you tell me the adjoint of A?
One.
1.
Sorry. Uh, minus
Actually,
one.
minus 1. Yes.
Uh, diagonal another one diagonal plus one.
Hmm.
Diagonal one. Zero, zero minus two. Second diagonal.
Here 0.
Minus two zero.
Minus 2, 0. Yes. So you know how to write like adjoint. Okay.
Yes, sir.
Now if you do product, okay, it will be 1. Just see this proof. This is a very famous theorem. So what it will be? I am just going to check. So determinant of A you know is minus 1, right?
Yes, sir.
Okay. So can you see that it is coming out to be minus 1? Yes. Right?
Yes, sir. Oh, minus one take common.
We can take minus 1 common, right?
Yes.
Yeah. So using Cramer rule, you know that using Cramer's rule or theorem, whatever it is, if you know what we are given, determinant A is not 0, right? This is our first statement.
Yes.
Then how can we write A? We know that A times adjoint of A upon determinant of A is identity, correct?
Yes.
And this is precisely the invertibility, correct?
Yes.
If a matrix has a left inverse, we saw that it has a right inverse above also.
Yes. A in S equal to IN.
Yes. So this implies A is invertible. So are we done with this theorem? What do you think?
Done, sir. Nice.
So it was a long theorem. The proof, yeah. So let us go back to the theorem again. Okay. We have seen the proof. So what is the most easiest way to check the matrix is invertible? The determinant, right?
Yes. Determinant zero.
Yes, like
Simplest
I am
way.
doing PhD and I am in my fourth year, I still use this first criteria to check the invertibility.
Mm. Yes,
Okay,
sir. Yeah, I
so
also use it. Mm.
yeah, so that will be there.
Linear independent case also use that idea.
Which one?
Linearly independent.
Yeah, that is also there. If the columns are linearly independent,
Column or row?
it doesn't matter.
Mm.
If columns are, see, you can always make columns into rows via transpose, right?
Yes, sir.
And transpose does not change the invertibility.
Yes.
Okay, is this
Yes,
clear
sir.
what I'm trying to say?
Yes, sir. Clear, sir.
Yes. So I am stopping for 2 or 3 minutes. If you have any doubt, please ask, because then we'll go to the Gaussian elimination method.
Okay, sir. Go again.
Okay. So it's better to start the Gaussian elimination method with an example. Okay. Have
Okay.
you heard this Gaussian elimination method?
Yes, sir. I think my UG course I was learned,
Oh, UG course you learn, huh? And that is
but
nice.
VG is not that subjective.
That is subjective.
Mm.
Okay. Okay, so we'll see one example. So, Gaussian elimination method, I'll first explain with an example, then we'll see the general algorithm. Okay?
Okay, sir.
So, I hope you are with me up until now. See, Thangeshwaran, unlike the previous classes, this is going to be a long one. Okay?
Okay.
So, I don't know, like, what is your responsibility as a student? I'm not aware because anyhow I have to teach. Okay?
Okay,
So
sir.
if you stay, it will be good. If you want to leave after 1 hour, that is also fine. Okay.
Okay, sir. Sir, last week class kindly upload.
I have uploaded the lectures on my YouTube channel. Okay. You just go there.
Okay, sir.
You have the
Lecture
link, right?
notes is not there, sir.
Ah, see, that is something that these NPTEL people should take care of, right?
Okay, sir.
Yeah.
Uh,
I'll ask. Okay.
okay.
Yeah. So we start with the one particular example, then we'll see the algorithm. Okay.
Okay, sir.
Or let us take a 5 minute break. Okay. I'll
Okay,
be
sir.
I'll be back. Okay.
Okay, okay, sir. I'm waiting.
So are you ready?
Yes, sir.
Okay, so let us start with the easiest of the equation. X plus y plus z is equal to 2. X plus 2y plus z is same as 5. Then 2x plus 3y plus 4z is 11. Okay, so this is a system of equation, right?
Yes, sir.
So are these linear equation?
Yes, linear. No doubt.
How do you know that these are linear?
Uh,
Is this linear now?
no.
No, it is not linear. Okay. Is this
All
linear?
the powers are one.
Is this linear now?
No, no.
Okay. So you know linearity, right?
Variable powers are one. If you
Variable
take
powers has to be 1. Correct. Correct. So what will be the system in matrix form?
uh,
The
1,
system
1.
can be written as one, one, two, right?
Yes.
1,
1 to
2,
3.
3, 1,
1 and
1,
4.
4. And column vector, the unknowns are x, y, z. And you'll have 2, 5, 11.
11.
Okay. So is this matrix invertible?
I have
So
to
I'm
check.
just computing the determinant, okay?
Yes. You have to find rank also.
5, there are various method, okay?
Yes.
3 minus 4, I think it is invertible. Oh, is it not invertible? Oh yeah, it is invertible, okay?
Yes.
Because it is, determinant is 2, correct?
Yes.
Hmm. So Gaussian elimination means, you know, you have to convert it into an upper triangular matrix. Okay? You have to convert this into an upper triangular matrix. And how do we do that? From linear algebra you must be knowing how do you do that? We first check whether this entry is 1 or not, right?
Below the diagonals are 0.
Yes, so below the diagonal we'll make it 0. So
Well,
R2 will go to R2 minus R1, correct?
2 minus 1. Yes. Okay.
RJ, you know na notation. RJ means the rth jth row. Sorry, what I'm
Death
saying.
row. Yes.
RJ means, okay. Let me just write one line. Yeah, it will be clear. RJ goes to alpha RJ plus beta RK, J not equal to K, means that we replace jth row by the row obtained by doing alpha times jth row, correct?
Yes.
By adding, actually I should have written by adding alpha times jth row and beta times kth row.
Okay.
Okay, so this is my notation. So as you are saying, we should have R2 goes to R2 minus R1 and R3 should go to R3
Two.
minus 2R1, correct?
Yes.
So this will be 1, 1, 1, then
0,
0,
1, 0.
1, 0, then 0,
0,
1,
1,
2.
2.
And here what you will have 2, 3, 7, correct?
Yes, 7.
You know why this is happening, right?
Yes, sir. Augmented matrix.
We'll see in the general algorithm also, okay?
Okay.
Because whatever changes you are making on left hand side, you have to make it on the right hand side also, correct?
Yes.
Now
I
what you
think
will do?
this matrix is augmented matrix.
This is called augmented matrix.
Yes.
Augmented matrix. Now what you will do?
Make third row second element 0.
So this you will make 0, right?
Yes.
So how will you do that?
Just R3 minus R2.
Very good. So and rest of the rows will be unchanged, correct?
Yes.
This is the beauty of this method, that the rest of the rows will be unchanged.
What method, sir?
This Gaussian method.
Okay.
So this will be 0 and this will be 2 and this will be 4, correct?
Yes.
So now can you find the solution? See, it is in upper triangular now, right?
Yes, sir. 2z 2z is equal to 4, then z is equal to
Just a minute.
unique solution.
Just a minute. Yeah. So you will have z is equal to 4 by 2, right? Which is 2, correct? Yes or no?
Yes, sir.
Then y will be 3, correct?
Yes. X is equal to x is equal to
And
no.
what
X
does
plus
this
y
read? This reads x plus y z is equal to 2.
2
So this implies
2
x plus
3.
5 equal to 2. So this implies x must be minus 3.
Yes.
So this phase of Gaussian elimination is called the backward substitution. Okay?
Yes, sir.
Why backward? Because we are getting, see, the last variable is getting the value first, right?
Yes.
So in that sense it is backward.
Okay. Suppose we make lower trigonometrics.
Hmm?
Suppose we make lower triangle matrix, then we get forward substitution phase.
Yes, you can do that. It is just a term, okay? The
Okay,
aim
sir.
is to solve the system. Okay?
Then why they are using upper trigonometries only?
Again, that is a convention. Okay? That is just a convention. In mathematics, you will see that things are done because of the ease of thing. I mean, what should I say in that? So, for example, we could have written equation like this, right?
Yes.
Do you get my point?
Yes, yes.
It would have conveyed the same meaning. Am I
Yes.
right or wrong?
Right,
But
right,
then,
yes, sir.
someone who did it first, we are following his convention.
Okay, sir. Okay.
Okay.
Okay, sir.
Now I will write the algorithm. Okay, and then you tell me whether or not it's clear.
Okay, sir.
And it might be a tedious thing. Okay. General algorithm. So you consider this system of equation a11. We will do it for only 3 cross 3. Okay. b1. So this thing is there. So it is a linear system in 3 variable, correct?
Yes, sir.
So we'll denote it by E1 means equation 1, E2 means equation 2, and E3 means equation 3. I hope that is not too confusing. Yeah. So please, if you have any doubt, please stop me.
Yes, sir. No doubt.
Step 1. What was the step 1? See, remember in this case, step 1 was making this to be 1, but it was already 1, right?
Yes.
So, if it had not been 1, what would we have done? We would have divided by the same number, right?
Yes.
Yes. But we can divide only when a11 is not 0. So this you have to take care. So step 1, if a11 is not 0, then define m21 as a21 by a11, comma m31 as a31 by a11. You note that these will be the coefficient in the next rows. See, this is what happens, right? Okay, I'll explain later. So what do we do? We obtain a new system as follows, which is equivalent. When do we say two systems are equivalent? When both of them represent the same linear equations, right?
Yes, sir.
For example, this equation and this equations, they are equivalent, correct?
Yes, correct.
Yes. Which is equivalent. as follows. So how do you do it? You retain matlab hold, okay? Retain even as it is. Retain even as it is. Then replace E2 by E2 minus M21 E1. Okay? And E3 by, see, these are the row operation that you will do. Okay, I'll explain now. See, you had this system of equation A11, A12, A13, A2. Oh god, I'm a terrible thing I did.
A2.
And then something is here also, right? B1,
B2,
B2,
B3.
B3. Now we know that A11 is not 0, right? This is not 0.
Yes.
So how will we make this entry 1? This entry 0, how will we make? We'll replace E2. Okay, let
Replace
us,
A1.
because we have used R1, we'll use R here only. So how will you do the computation if you were to make it 0? See, you will divide R1 by first A11, correct?
Yes.
And then you will multiply it with by A21. Am I right or wrong?
Yes.
So that when you subtract it, it will become 0. This entry will become 0. Am I correct?
Yes.
And similarly, what you will do for R3, tell me.
R31.
So you will divide it by
R31 divided
A11
by
and
R1.
A31, right?
Sorry, A31. Sorry, A31 divided by A1.
Yeah. So then what you will get? You will get A11, A12, A13. All these are unchanged. But here you will have 0, correct?
Yes, sir.
And here you will have something which will be, let's say, denoted by this.
A22.
Okay?
Okay.
Something that we don't care. I mean, you know something will be there.
Yes.
Then here also you will have 0, right?
Yes, sir. A322. A332.
And here you will have B22.
B32.
Yeah. So in equation, what does it mean? That A11 x1. Should I write this equation?
No need, sir. Going to next iteration.
Okay, let me just write for this one. For next time I will not write, okay?
Okay.
Okay, so let this system be 2. Let this system be 2 and the original system be 1. So can I say 1 and 2 have same solution?
Yes. Yes, same solution.
Yes, and this is really important, right?
Yes.
Why this is really important? Because we are trying to solve system via easing our computation, correct? So
Yes.
if at any stage the solution change, then our computations are useless, right?
Yes.
Has same solution set. Yeah, so this is to be noted. Huh? This is really important. This is really important. Now, what do you do? Step 2.
Make A3120.
Yes. So, let this is not 0. Huh?
Yes. A2290.
Yes. Then what will you do? What operation you will play? R3 goes to,
R3 minus
so you will divide R2 by A222 and
A222
then multiply it by,
A312.
yes, exactly. So this is precisely we define, okay, this coefficient we define, okay, there is no need to actually, then you'll have something A11, A12, A13, correct? Here you will
Yes.
have 0, again this will not change, only those rows will change on which you are applying the row operation. Now it will
Yes, sir.
become 0 as it should be the aim, and then
A3
3, yes,
3. Yes.
then it will be B1,
B23
B22,
3, sir.
no, second row there is no change, no, it
Yes,
will
yes,
be,
yes, yes,
yeah,
yes, yes, yes. Okay, sir. My mistake.
yes. So hence we have an upper triangular form. Is this correct?
Yes, sir, correct.
Yeah. So this method is called the, this method that we have solved is called the naive Gaussian elimination method, okay?
Okay, sir.
Naive. Naive means, what should I say? Not very wise, okay? Do you know why?
I don't know, sir.
Because this method is not foolproof, no? Like this is not bulletproof method.
Oh,
First of all, we have two assumptions. First is this A11 is not 0, correct?
yes.
And second, what did we assume? That this A22 is not 0.
Yes. Here, zero is also possible here.
Yes, here you can have 0, right?
Yes.
But we also know how to deal with that solution also. Because you have done certain linear algebra, right?
Okay.
Yeah, so a very remarkable thing I would like you to note. Remark. First thing first. If you define your U to be this matrix, you know, the matrix that we have, this matrix. The final matrix, huh?
Yes, sir. A333.
Yeah. And you know this coefficient we assume M32. We have two more coefficients above also, right? You remember
Yes.
those two coefficients here?
A21.
How are these coefficients coming into the picture? These are precisely these coefficients, right?
Yes.
Yeah.
A21 minus A21. Yeah.
Yeah.
There will be.
So, and then you define a lower, U for upper triangular, L for lower triangular, okay? You define this 1, M21, M31, M32,
M32.
1, 1, 0, 0, 0.
0, 0.
Okay? Now I will do some computation which might be boring, but it will be very interesting to see what happens. Okay?
Okay, sir.
I will compute. So we will be computing LU. Okay? and this might be the motivation for the next few lectures when we'll be reading LU factorization. Okay.
Okay, sir.
So LU, when you multiply, what do you get? So it is the first row 1. Okay, step by step we write.
Matrix, yes, sir.
Are you sure?
Sure.
How did you do the calculation? Huh, Thangeshwaran, or are you just bluffing?
No, sir. If you substitute M21 and 31, then matrix multiplication we get.
Exactly. This is just we are reversing back, right?
Yes.
If you look closely, we are just going back.
Yes, it's going back.
How did we reach U? Via some operations. This LU means we are going back. So we'll have first row as, I'll write quickly. We'll have A11, A12, A13, right? The first row.
Okay, sir.
Then you'll have M21, A11.
Zero. Remaining 10.
No, M21, A11. This is correct, right? Oh, yeah.
Some plus 0.
No, but I won't write plus 0.
Okay.
Then you will have M21, A12 plus A22, right?
2. Okay, sir.
And here you will have M21, A13 plus A23, 2.
1. Two.
Is this correct?
Yes, sir. Correct.
Now you will have M31, A11.
M31, A12.
Yes.
Some plus M32,
Okay, I will write in the
A22.
next line. Okay. M32,
A22.
and here we'll have some very
Next.
amazingly ugly expression.
Yes. M31, A13. M32, A23, 2.
And plus something
A3.
also.
A3.
Yes, plus.
A33.
Okay. Now remember, what was M21? M21 was A21
divided by A2. A1.
Okay.
Yes.
So this row is fine, correct? First row is fine. M31 was A31, A11. Okay. So if you write again, then you will get A11 as it is, A12, A13. What will be the next entry? It will be A21, correct?
Yes.
Yes. And it will be A11 plus A222, correct?
Yes.
Then what will it be? Okay, here you will have A31, right?
Yes, sir.
Yeah. So, okay, let us write star, rest
All
of, they are same, okay, the previous one. Or should I copy? I can copy in the tab, no? Why I'm bothering so much? So is this fine? I warned you in the beginning it is going to be a bit tedious. So up until now is it fine?
Yes, sir.
Yeah. So let us compute this like this entry A2 M21 A12. This is the entry, right? I mean this column is fine and this row is fine, right?
Yes.
So M21 is A21 A11 then A12, and let's go to A22 2. How did it come A22? It come like this, right? Here it came, correct?
Yes.
So what it should be? A22 should be, follow the operation, it should be A22 what I want to say is the following. A22 it will be A22 minus A21 by A11 times A12, correct?
Yes, sir.
Yeah. So just keep that in mind. Oh, so this is actually A22 minus A21. What is there? A21. See, this is precisely A22, right?
Yes.
Yeah. So you solve each one of them. Okay, you know how to get the values back, right?
Yes, sir. Similar.
Proceed further and show that. So you were right in the beginning. Your intuition was correct. That LU is indeed same as A.
Yeah.
And this is called, later we'll see, this phenomena is called LU factorization of A. Lower triangular and upper triangular, okay?
Yes, sir. LU decomposition.
Yeah, LU decomposition or factorization, same thing, okay?
Okay.
Okay, now see, because this is a method, so it will have some drawback, right?
Yes. First term on
So we will
zero.
see the drawbacks of, let D with the capital, drawbacks of naive
Gaussian elimination.
Gaussian elimination method. In the process, we made certain assumption which we have just also discussed, right?
Okay, sir.
So example 1, let's say example 1. So Thangeshwaran, what do you do? Are you a student?
No, sir. Stop.
Oh, okay. Where do you teach?
Guest lecturer.
Oh, okay, okay. Which college?
Government college. Government
Oh, okay.
Arts and Science College, Tamil Nadu.
Oh, okay, okay, okay. So consider this system of equations, okay?
Okay.
I am going to write something and you just tell me whether or not you can apply Gaussian elimination. Can you apply?
Yes.
How?
No. First term is zero.
Exactly. The step 1 cannot be started as A11 is 0. See, why? Now you must be thinking, okay, what the big deal? We can interchange the rows, right?
Yes.
But see, the point of numerical analysis, one point is you should think like a machine. Okay? Machine does not have its own brain, right?
Yes.
So we will give it some steps to do, which we call as an algorithm. Correct?
Yes, sir.
So it won't interchange these two rows unless and until we ask it to do. Are you getting my point?
Yes, sir. Once again.
See, what I am trying to say, you might feel okay, Gaussian elimination will work if we interchange the rows. First row by second row. Then this method will work, right? If we interchange
Yes.
the rows.
Uh, yeah.
You just interchange the row, like 1,
Yeah,
1,
yes.
0, 1, and
Yes,
then
sir.
2, 1, right?
It comes under row operation.
Yes. So,
Yes.
yes, it comes under row operation. You can interchange two rows. Okay.
Yes, yes.
Now,
Around.
what I want to emphasize is the following, that when we are doing numerical analysis, it means we are using machines to do the computations.
Okay, sir.
Now, if we are setting a Gaussian elimination method as we have done earlier, the machine will say the method cannot be started. Yes or no?
Yes.
It won't be thinking like this, okay, let's interchange the rows. No. Unless and until we add that step in the algorithm, it won't do that on its own. So that thing you should keep in mind. Okay?
Okay, sir.
Yeah. So thus, okay, I should write naive Gaussian elimination. So this is one drawback of this naive Gaussian elimination method. Now another example we see. Yeah. Can you mute your mic when you're not speaking, Thangeshwaran? Because it creates a lot of disturbance.
Okay.
Okay. Now we'll see something. Let epsilon be between 0 and 1. Okay, epsilon is very smaller than 1. This double less than means small, okay? And again it means very small.
Strictly.
No, not strictly. It means very small.
Okay.
Small, very small. Okay?
Okay, sir.
Yeah. So consider this system of equation. Consider the system. You know, epsilon 1 1 1. So have you noticed what we are trying to do? We just replace 0 by a very small number, right? Yes or no?
Yes, sir.
Yeah. Now since epsilon is not 0, which means we can apply step 1, right?
Yes.
We can apply the step 1. So can you tell me after step 1 what we'll get? We'll get epsilon 1, epsilon inverse, 0, 1 minus epsilon inverse, right?
Yes, sir.
And 2 minus epsilon inverse. Am I correct?
Yes, 2 minus sir.
And the backward substitution, what will it imply?
One minus epsilon inverse x2 is equal to.
Yes. x2 is same as 2 minus epsilon inverse upon 1 minus epsilon inverse. And x1 is
Epsilon x1 plus
epsilon inverse 1 minus x2, right?
Yes, sir. Yes, sir.
Yes. Okay, now see, now I want to think like, so when epsilon is very small, right?
Yes.
So this epsilon inverse will be very big, correct?
Yes. If you take epsilon is equal to 1 by n, then
Exactly, it is very big. So what computer will do, this is just the computer evaluates, because computer has certain approximation, right, in its system.
yes.
So it will evaluate 2 minus epsilon inverse as minus epsilon inverse, correct?
How, sir?
Because see, 2 minus very big number, very big. It will be, for it will be same as minus a very big, right?
Yes. Yes.
Do you get my point?
Sorry, sir. Once again.
Like, see, this is a very huge number, okay? Minus
Yes.
epsilon
Yes.
inverse, it's a
Yes. Big.
negative of very huge number, correct?
Yes. Big natural
Very,
number.
very, very big in negative. So whether you
Yes.
add 2 or any number, it doesn't matter, because it is already a very big number.
Yes.
So
Yes.
approximately it will be same as minus epsilon inverse.
Oh. Okay.
Do you get it now?
Yes, sir. Yes, sir.
Yeah.
Now I get.
And similarly,
It comes from real analysis, sir. This idea.
this logically you can think of it like the limiting argument, okay? Because
So
as
epsilon Archimedean
n goes to
property.
infinity, n plus 2 also goes to infinity, like this, right?
So Archimedean property
No,
are
I'm
okay.
not saying Archimedean or anything. I'm just giving you one explanation what happens in the computers.
Okay,
Okay?
sir.
Yeah. So just and it will happen, okay?
Okay.
So then this will be same as minus epsilon inverse. I hope you know why. Like logically you can feel it, right?
Yes, sir. I feel.
Yeah. So according to this, what will be x2? X2 will be, x2 was this. So what will be x2
Next to
equal
one.
to? 1, correct. And what will be x1?
X. mm,
It will be 0, right?
Yes, 0.
But is 1 and 0 the solution? However, what I want to say, however, the exact solution is this. Okay?
Sir, how x1 equal to 0?
See, this is some finite. This is x2 is 1 now, so this will be 0.
Yes.
And epsilon inverse is also very,
Very big number.
but in that sense it will be finite. Okay, but when you so first it will evaluate backward substitution, correct? So first it will say x2 will be 1. This approximation, na?
Yes.
And then it will put 1 in this value, okay?
Yes.
So it will become 0,
Yes, sir.
okay?
Yes, sir. I understand.
Yeah. But if you check, if you, however, the exact solution is, given by x1 is 1 upon 1 minus epsilon, which is clearly not 0, right? And x2 is, so if epsilon is very small number, then approximately it should be 1, correct? And x2 is 1. These are the exact solution. If you compute, the exact solution will be this.
Yes,
And
sir.
if epsilon is very small, then again it is 1. So in this particular example, what we are saying, that if you use backward substitution, if you use naive Gaussian elimination, the answers are wrong, correct? Do you get the point? See,
Sir,
computer
once
will
again.
give you this, okay? Hello? Yes, what is the doubt?
Sir, I can't get your points.
Sorry?
X2 I can't understood.
No, ask clearly.
Sir, X2 is equal to 1.
No, I am
Okay.
not saying x2 equal to 1. I am saying the exact solution will be 1 upon 1 minus epsilon and 1 minus 2 times epsilon upon 1 minus epsilon if you solve. Okay? If you
Okay,
solve
sir.
this system, okay?
Okay.
See, but machine also did approximation, so we can also do approximation, right?
Yes, sir. Yes, sir.
What does
Approximation
machine
correct.
approximation give us? 1 comma 0, correct? This
Yes.
x2 to be 1 and x1 to be 0. With the same logic as machine have used, if we apply that logic on our exact solution, so since epsilon is very small, so denominator will be 1, right?
Yes, sir.
So ultimately x1 will be 1
One.
approximately.
Yes.
And if with the same logic x2 will be 1, correct?
Yes.
So what is happening, using the same approximation technique we are getting the wrong solution.
Yes. Wrong solution. X1, X2,
Exactly.
1.
So
Yes.
in this particular example, so there also this naive Gaussian method fails, okay?
Yes.
In this,
Of
so
course.
this is a very good example to teach how things differ in machines and in reality, okay?
Okay, sir. Okay. Nice example.
The solution in this particular example, the solution obtained by the Gaussian elimination is completely wrong. You see, it is completely wrong.
Yes.
Completely wrong. Okay, so if for example if you want to you can choose, if you want to understand this example better, you can choose your epsilon to be 10 power minus 3, okay, and use 3 digit rounding. You will see, okay, 3 digit rounding, correct? Hello?
Yes, sir. Yes, I got you.
So you
Complete.
just put, if in your free time what you do, you just put epsilon equal to 10 power minus 3 here
Okay.
and do 3 digit rounding, and you will see why
We,
this is
we,
wrong.
we get 0.
Okay,
Okay.
so because that was pure logic, but concretely you just take this epsilon and work with it,
Okay.
and this will give you a better feeling of what I just said.
Yes, sir. Yes, sir.
Yes.
And I understand.
Okay, just a minute. I'm just thinking what
Okay,
else
sir.
there to cover. Meanwhile, if you have any doubt, please think of it and ask. Okay.
Okay, sir.
Okay. So this method fails. Clearly, this method fails, right? I mean, this naive Gaussian elimination method is failing miserably. This much you agree? Am I audible?
Sir, audible.
Yeah. So even you see in the example one, the Gaussian, it is the simplest of the 2 cross 2 system, right? Even in that case, Gaussian elimination fails. So when something fails, it does not mean it is completely wrong. This Gaussian elimination might work in some cases, right?
Yes.
So we don't need to eliminate this method. What we need to do is to modify this method, right?
Yeah.
So let us do what we call as modified Gaussian elimination method. So I will just give you the idea, okay?
Yeah.
Modified Gaussian elimination method. See, what was the first problem? See, you tell me. We wrote this system. Mm, yeah. So we had this system. So what was the first step? We assume B1 A11 to be not 0, right?
Yes.
But it can be 0, right? So
Can be. Yes.
if A11 is 0, see, now I am going to write one thing. You just tell me, okay? Whether or not it's true. Let S1 to be maximum of modulus of A11, A21, mod of A31, right? Can it be 0?
No.
Because see, this matrix A will always assume that we are working with invertible matrix, okay?
Yes. So that S1 is non-zero.
Yes. So this will always be strictly positive, right?
Yes. Sure.
So let k be the least integer, k be the least integer such that mod ak1 is s1. Okay.
Yes, sir.
For example, is a11. For example, if first column is this a, so what should be your s1? It should be mod a21, right?
Yes, sir.
Yeah. So now if now we you interchange. So step 1. This is where this method is modified. Now you interchange r1 with that row rk. Okay?
Okay, sir.
Right. So you will get some new system, correct?
Yes, new system, new matrix.
New matrix. We don't know, but definitely we'll have a new matrix.
Yes. So previous matrix and this matrix are equivalent or not?
Obviously, when you interchange, it doesn't change the solution, right? We
Solution
just
not
solution will
change.
not change, correct?
Solution will not change, but
Yes.
matrix equal.
No, equivalence means, what does equivalence means? That one can be recovered from another, okay?
Okay, sir. Okay, sir.
As I said,
Not equal matrix. Yes.
not equal. They won't be equal, but they will be equivalent, okay?
Equivalent.
Yeah. Now see here, what can you say about this matrix? This will always be not 0, right?
Yeah, clearly non-zero. Positive.
Not positive. We are taking modulus, okay? So it can
Oh,
be
okay,
negative.
okay. So,
So now here you can apply the step 1 of naive Gaussian elimination, right?
yeah.
Yes or no?
Yes, sir, we can apply.
So the problem at the first step of the Gaussian elimination can be removed. Yes or no?
Remove. Yes, sir.
So now apply
Yeah,
step
we
1 of naive Gaussian elimination method. Okay,
okay, sir.
is this clear?
Clear, sir. Yes, sir.
So again you will get some matrix. What will you get? You'll get
Submit
first matrix, first row unchanged.
and change second matrix.
Here you will have 0, 0. Then
A
here you
two.
will have something, right?
Yes. 0.
Is this clear?
Yes, sir.
Now what will you target? See,
A32 will be
you will
there.
make 0 with the help of this, correct?
Yes.
But it was working again. Assumption was that A22 is not 0, right?
Again A22 now.
If A22
And
is not 0,
I I don't know.
then proceed with naive method, okay? Correct?
Yes. Yes.
Naive Gaussian elimination method. But what about if it is 0?
Take maximum observed value A22 and A32.
Yeah, if it is
Two.
0, then you just interchange R2 and R3, okay?
Yes.
And then you will have, because see, just a minute. So in general, you will take S2 to be and something, okay?
Yes. Maximum
Maximum of
A222 modulus A22.
comma mod A32.
Yeah.
Why it should be not 0?
Both are uh,
If both are 0,
maximum value.
if maximum is 0, this means both are 0, correct?
Yes. But matrix is determined non-zero. A invertible matrix.
No, but invertible matrix, this can be an invertible matrix, right? 1, 0, 0, 0, 0, 1, 1.
This is
Yeah,
not
exactly.
answer.
See, this is the problem, right? See, if this is something, you have 0 here, then this is something, 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 something. If it is also 0, then determinant will be 0, correct?
Yeah.
Because for upper triangular matrix, determinant is just the product of the diagonal entries,
Yes.
and you will have 1 0 here. Okay?
Okay.
So then so let L be the smallest integer such that SL is mod of AL to 2. Okay?
Okay.
Then you know what to do, correct? Then what you will do, you will interchange R2 with that particular row, RL.
RL.
And how will the system be then? See, first row will be unchanged. This we know, right?
First row, second row also. And,
No, second row we are doing something, right? This 0 will be there.
yeah,
Then
yeah.
it will be some A223,
Okay.
A233. Are you getting my
Yes.
point?
Yes, sir. Yes, sir. I come to smoothly.
3.
Yeah. Again,
See,
do
now this
operation.
part cannot be 0, right?
Yes, sir.
So apply step 2 of Gaussian naive method, naive version, okay?
Yeah.
See, I'm writing explicitly everything so that everything is clear when you look back, okay?
Okay, sir. Okay. Once again, I
Now, if
review.
you apply Gaussian elimination, so this will, this row will be unchanged, correct?
Yes,
First row
sir.
will not be, this will become 0, this will become 0, this will become 0, correct?
Yes, sir.
Now here you will have something, like let's say A22, this row will also be unchanged, right?
Yes, sir.
See, remember A11 was not 0. That was the assumption. Like that's how we define the method. So this is also not 0. This is not 0, right? This is
Okay.
also not 0. Okay?
Okay, sir.
And here you will have some now fourth stage.
Fourth step. Uh, Suppose A330, sir.
Then again it will not be invertible, right?
Yes.
Because one entire row, the last row is going to be 0, so determinant will be 0.
Yes.
So since A is not invertible, A is invertible, A334 is not 0, right?
Yeah.
Now, then what will it imply? X3 will be B34
Divided by
times
A34. A33.
A334, right?
Yeah.
Then X2 will be
Mm.
B23 minus X3
8.
A233 1 upon A223, right?
Yeah.
And X3 you know. X3 you know, right?
Yes, sir.
This value you know already from this one
Previous step.
previous step. Now,
Right.
third is
X1 1 by A11.
x1 will be 1 by
100 A11.
A111
B11 minus
B11 minus
minus
x2 A121
A12
minus
minus
x3.
X3 A13. Yeah.
So again these two value you know.
Yeah. Previous two steps.
So what are we doing? We are again using backward substitution, right?
Backward substitution.
So now this method works, right? For invertible matrix.
Yes, sir.
This method has no problem as long as we are dealing with the invertible matrix.
Invertible
Okay?
matrix. Yes, sir.
So just add one remark. Modified Gaussian elimination method works on invertible matrices. Okay?
Yes, sir.
So is this understandable what we did today?
Yes, sir. I understand, sir.
So if you have any doubt, please ask. Otherwise,
Very nice explanation, sir. Your class. So that I have no doubt.
see all these things it takes a lot of time to write. Okay,
Yes, sir.
but
Yes, sir.
when you, for example, if you look the notes.
Yes, sir. I feel confident your lecture.
Oh, really? Thank you. That means a lot. But notes should be very proper. Okay.
Yes, sir. Yes, sir.
Yeah.
Very properly.
Yeah. Yeah. So okay, if you have no
Yes.
doubt, then maybe we should end this meet. Is this
This is
fine?
sir.
If you have no doubt, then I am ending this meet. Okay.
Yeah. Okay, sir. Okay, sir. Sir, I want notes, sir.
Oh,
How
you
to?
want notes, huh? I'll ask these NPTEL people to forward. Okay. I don't know what is happening. Okay.
Okay, sir. Link also is not there, sir.
Okay, I'll talk to them. Okay, if anything does not happen, then I'll forward you personally. Okay.
so that some students are not there.
Yes.
I think
Okay. Okay, Thangeshwaran. Bye.
it's a best.
Bye.